Welcome to the presentation about calibration of interferometric data in general and ALMA data in particular. My name is Katharina Immer, and I will lead you through this presentation today. In the first part of this video, I will summarize the calibration basics and answer the following three questions. Why do we need to calibrate our data? What are the calibration steps? And how do I know that the calibration was successful? In an interferometer, each antenna observes a signal from the astronomical source. Then, the data are combined in the correlator on a baseline basis. Here, the interference pattern is generated. Due to the orientation of the source with respect to the telescopes, there is a delay in receipt of the signal at one compared to the other antenna. This is called geometrical delay. For constructive interference and a maximum signal in the correlated data, the two antennas must be synchronized. In the ideal case, only the geometrical delay must be compensated. The data received at the antennas have both amplitudes and phases. To increase the signal-to-noise and the UV coverage, we want to integrate the observed signal in time and over a certain frequency range. Thus, the phases of the correlated data must be zero and the amplitudes flat. Otherwise, the coherence is lost. However, in a real interferometer, there are different sources of error which affect the phase stability and the amplitudes of the data. These are, for example, imprecise positions of the antennas as well as the observed sources, which lead to errors in the delay term, the atmosphere, which perturbs the wavefront and leads to phase changes over time, and the electronics, which can introduce amplitude errors. This is the complete radio interferometry measurement equation, which entails all the sources of error which affect the true visibilities of the source. The interferometer records the observed visibilities, but we are of course interested in the true visibilities. Thus, we have to solve for these different parameters. This is what calibration does. For this to work, we assume that the calibration parameters are antenna-based and that the time and frequency effects are independent. In the real case, the previous diagrams look more like this. In the amplitude versus frequency panel, we can see the bandpass shapes of the receivers. In the phase versus frequency panel, the instrumental delay leads to jumps between spectral windows, and the atmosphere introduces a slope. The amplitude versus time is not flat if the source is observed at lower elevations or has intrinsically varying flux. The atmosphere leads to rapidly wrapping phases with time. However, target sources are typically faint, so that the data are dominated by noise from the full primary beam of each antenna. So we need to rely on calibrators to calibrate the target data. There are typically three different types of calibrators that we observe in a project. These are the bandpass calibrator, the flux calibrator, and the gain calibrator. The bandpass calibrator has to be a strong point-like source, normally a quasar, to correct for the bandpass shapes and the instrumental delay. The flux density of the flux calibrator has to be well known to be able to determine the absolute flux density level of all the other observed sources in the project. This calibrator either is a quasar whose flux density is being monitored, or a solar system object for which a well-determined flux density model needs to exist. These two calibrators can be anywhere in the sky and do not need to be close to the target. They are usually observed only once per project for some minutes. The gain calibrator has to be a point source located close to the target on the sky, so we can apply a technique called phase referencing. For phase referencing, we have to observe a strong point-like source within a few degrees of the target on the sky. The gain calibrator has to be close enough to the target so that it is affected by the same part of the atmosphere and thus shows the same phase variations as a target. To calibrate the phases and amplitudes of the target, the corrections of the gain calibrator are interpolated and applied to the target. The phase referencing cycle, which means switching between observations of the gain calibrator and the target, has to be fast enough to trace temporal changes in the atmosphere. A point source is by definition unresolved on all baselines. That means that the amplitude is the same on all baselines and flat with time. All sky brightness comes from one single point. That means that the phases are zero as a function of baseline and time. Furthermore, the selected calibrator should have either a flat spectrum or a known spectral index and do not show any flux variation with time. Bright sources are selected to be able to achieve high signal-to-noise ratios in a small on-source time. Interferometry data calibration follows 3 simple steps. First, the effects of the instruments, like the bandpass shape, variations in receiver's noise, and corrected antenna positions are removed, using the bandpass calibrator and information from water vapor radiometers. Then the atmospheric influence is being removed using the phase calibrator, and the amplitudes are scaled to the correct flux values, bootstrapping the correction values from the flux calibrator. In the last step, residual time-dependent corrupting effects are being removed, using the target itself. This technique is called self-calibration and is being discussed in a video later today. We start the calibration with the purely instrumental effects. The bandpass shapes in the amplitude versus frequency panel should remain constant during the whole project, since they have an instrumental origin. We can correct for them since the bandpass calibrator either has a flat spectrum or a known spectral index. In the phase versus frequency panel, we can see the jumps between spectral windows, which is a pure instrumental effect due to different light paths. These are constant for the whole observation. The slope is an effect of the atmosphere. We can correct for these effects since the bandpass calibrator is a point source and thus should have 0 phases as a function of frequency. These corrections are then applied to the other calibrators in the target. This is called bandpass and instrumental delay calibration. The visibility amplitudes from the correlation have arbitrary scaling. We use either a strong point-like source with known flux density or a solar system object with a good flux density model to convert these amplitudes into physically meaningful values. These scaling factors are then applied to the other sources. This is typically a 2-part process, where the amplitude scales are set with one task, for example Sedjansky and Casa, and the fluxes of other sources are then scaled with another, for example flux scale in Casa. With a gain calibrator, we can calibrate the effects of the atmosphere on the phase stability. Since a gain calibrator is a point-like source, the phases should be 0 both in frequency and time. During phase calibration, we fit the slope of the phases simultaneously in frequency and in time. These corrections are then applied to the gain calibrator itself to obtain flat phases at 0. If the amplitude of the gain calibrator is changing over the time of the observation, the self-calibration method can be used to obtain flat amplitudes. Once we obtain the corrections from the gain calibrator, we can interpolate them and apply them to the target. Now all observed sources are calibrated. After obtaining all calibration corrections, one should check the data of the calibrators before and after applying those corrections to verify that the amplitudes are flat and the phases 0 in frequency and time. If this is the case, the calibration was successful. This table summarizes which calibration corrections are applied to which source. The flux scaling, obtained from the flux calibrator, is applied to all other calibrators. The bandpass, obtained from the bandpass calibrator, is applied to all sources. The phase and amplitude corrections are obtained from each of the calibrators and applied to themselves. The phase and amplitude corrections from the gain calibrator are applied to the target. In the second part of this video, I will show the relevant plots that were generated during the calibration process to verify that the calibration was successful. I will quickly show where the plots can be found if the data has been calibrated manually, but then focus on the pipeline calibration and the Weblog. Older datasets have been calibrated manually using the script for calibration. At the beginning of the Python script, the different calibration steps are listed. When running this script, calibration plots are saved in the QA folder. These are similar to the ones now produced by the pipeline, which will be discussed in the remainder of this video. The scripts produced by the pipeline are called Casa Pipe script and Casa Pipe Restore script. The former includes all pipeline processing commands that were run on the data. The latter restores the data, which means that rather than rerunning the pipeline calibration commands, it uses previously derived calibration and flagging tables and applies them directly to the raw data, producing a calibrated measurement set. The Weblog can then be found as a compressed file. After uncompressing it, one can open the index file in a browser. The main page of the Weblog gives a summary and overview of the observation as well as the pipeline. Here, one can find the CASA version that has to be used to rerun the pipeline. On the bottom, there is a list of the calibrated measurement sets, as well as a summary of the observations, including the ALMA band that was observed, the number of antennas, the observation start and end times, the on-source time, the minimum and maximum baseline length, and the size of the datasets. Clicking on one of the measurement set links, one gets to the measurement set overview. This page has a lot of information about the observations of this particular measurement set. For example, the spatial and spectral setups, the antenna setup, a list of the scans, or the weather. In the upper right corner, one finds the intent versus time plot. This plot shows when the different calibrators and the target were observed, as well as when pointing observations were performed and the water vapor was measured. In this example, the Flux and Bandpass calibrators were the same source, observed at the beginning of the observations. The gain calibrator and the target were observed alternately, as shown at the bottom of this plot. On the measurement set overview page, one can also see how the weather behaved during the observations in the PWV plot. This plot shows the measured precipitable water vapor over the length of the observations, color-coded for each of the antennas. In the example, one can see that the weather was stable with water vapor values between 1.1 and 1.3 millimeters for most antennas. Back on the measurement set overview page, one can have a look at the antenna setup, where one can find plots of the antenna setup itself and the UV coverage, as well as further details about the antennas and the baselines. This plot shows the configuration of the array, plotting the positions of the 44 antennas that were involved in the observations. The UV coverage plot shows the resulting UV coverage of this project. The UV coverage shows how well sampled the UV plane is and is important to understand the dirty beam and dirty map, which will be discussed in the imaging video later today. In the upper left corner of the weblog, there are two tabs called By Topic and By Task. Under By Topic, one can find the warnings and errors that occur during the pipeline run, as well as a summary of the flagging that was performed during the calibration. The values in the cells are percentages, which means that 100 is a fully flagged spectral window for an antenna. The By Task tab gives a list of all calibration tasks that were run. Here, one can find more information about each of the calibration steps. Each task gets a QA score assigned, which gives a quick insight into any problems that occurred during the task. On the right, the duration of each task is listed. I will now show some of these tasks and the corresponding plots in more detail. The system temperature represents the added noise in the system from the sky and from the receivers. The task tsyscal gives a first-order correction for the variation in sky and receiver noise as a function of time and frequency. In the plot on the right, the system temperature is shown as a function of frequency, color-coded for each antenna. The pink line on top shows the atmospheric transmission at these frequencies. There is a clear atmospheric line visible, which increases the system temperature at that frequency. The calibration corrects the amplitudes of all observed sources for the opacity of the atmosphere and these fake line features. Variations in the amount of water vapor across the atmosphere cause random delay differences, which lead to phase fluctuations on short timescales. Measuring the water vapor content with radiometers and applying an atmospheric model, the atmospheric phase fluctuations can be determined and corrected for. The plot on the right shows a deviation from the scan median phase where there's a scan number. The gray data are the uncalibrated data, while the red and green data show the corrected data. One can see that the phase noise decreases after applying the correction. This calibration has a higher impact at higher frequencies as well as at longer baselines. If the calibration does not improve the phase noise in the data, the pipeline will not apply the corrections. To verify that the bandpass calibration was successful, one should check the plots in the bandpass flag task as shown on the right, where the amplitude of the bandpass calibrator is plotted versus frequency. After applying the calibration, the amplitudes are flat. Furthermore, one should check that the phases are flat and close to zero as a function of frequency, as shown here in the plot on the right. With the task set models or set Jansky, the flux densities of the flux calibrator are set, using a model for the source. On the left, the modeled amplitude versus baseline distance are shown. On the right, the corrected amplitudes are plotted. One can see that they cluster around the model value of 2.95 Jansky. With the task G-flux scale, the flux scaling factors from the flux calibrator are applied to the bandpass and phase calibrators. In the plot on the right, the pipeline-derived flux density is compared to the catalogued flux density for the phase calibrator. An absolute flux error of about 10 to 15% is expected. Since a gain calibrator is a point source, we expect its phases to be zero as a function of time and frequency, and its amplitude to be flat. The phase and amplitude corrections determined from the gain calibrator are then interpolated and applied to the target. These are plotted in these two images here. In the last step of the secondary calibration, all determined corrections are applied to the calibrators themselves, which should then reproduce flat amplitudes and zero phases as functions of frequency and time, and to the science target. In the two plots on the right, the corrected amplitude and phase of the phase calibrator are plotted. In this project, the phase calibrator was quite weak, less than 0.05 Jansky, which lead to noisy phases. However, one can still see that the phases are clustered around zero. In the amplitude versus frequency plot, there is still a fake emission line visible, which is caused by the atmospheric line at that frequency. As a function of time, the amplitude should be flat and the phase is zero, as one can see in these plots here. Since both the phase calibrator and the target are weak, the phase noise is large. Finally, one can have a look at the amplitude versus frequency plot for the target. In this example, there are several emission lines in the spectrum. At the position of the atmospheric line, the amplitude is slightly increased, possibly due to the not corrected line in the gain calibrator data. To improve the calibration, we can tweak the pipeline. In this case, extra flagging is needed for the atmospheric line, which can be added in the flag template.txt file in the calibration folder. Then the pipeline has to be rerun. More information about how to tweak the pipeline can be found in this presentation by Ri Miurua from NAOJ. If you have any questions or need help with your data, please do not hesitate to contact us at our email address alma@strw.leidenuniv.nl. We are always happy to help.